Let's say this is a blood vessel, and it's made up of these endothelial cells, the same way that all blood vessels are. And let's say that this blood vessel gets into a fight, and it gets a little bit hurt. So the walls break open, and the cells now no longer seal the vessel from what's around it. When this happens, we wouldn't want all the blood in this vessel to come pouring out of the vessel, because we'd lose way too much blood. And so the body has a method of containing the blood. The first thing that's going to happen is that little platelets which are circulating in the body are going to come and deposit there and form an initial plug. So these little things are platelets. But it turns out that this plug is not quite solid enough, and so the body needs a second mechanism to solidify the plug. And that mechanism is what we're going to talk about most in this video. And I'm drawing that mechanism here. What I'm drawing is little fibrin strands, which will come and act as a kind of mesh to hold the platelet plug together solidly. So what do these fibrin strands look like? Well, they're made up of little fibrin subunits. And these are actually what we refer to as the fibrin molecules or proteins. And these, it turns out, have a natural affinity for each other, so that when you bring them together, they form a polymer. They join end to end, and they create a fibrin strand. So the question then becomes, how do you make sure that these fibrin units only join together and make a strand at the site of injury? So for example, if you had a bunch of little fibrin molecules over here, how would you keep them from joining together? And the answer is that you can't, which is why you don't have fibrin circulating in your blood. You actually have something else, which I'm going to draw here. And that something else is fibrin, but plus an extra piece. And that extra piece, as you can see, covers one of the active sites of the fibrin and therefore prevents it from joining to itself. So the name of this thing is fibrinogen, probably because it will form fibrin, hence the fibrinogen. And it's only when you convert fibrinogen to actual fibrin that the units can join together and form a strand. And so again, to repeat, you don't have fibrin circulating in your blood. You actually have fibrinogen. So the question then becomes, how does your body know to convert fibrinogen into fibrin at the site of injury? And the answer is that when you injure your endothelium here, you're going to expose your blood to new proteins. And maybe your actual endothelial cells will release some proteins because they're damaged. So basically you have new proteins that weren't seen before and that are seen now. And those proteins will eventually cause fibrinogen to turn into fibrin. So while evolution was designing us, it could have said, let's use these little yellow guys to convert fibrinogen to fibrin. And that might have worked, but it's actually not the most efficient way to do things. And the reason is, imagine if you and a couple of friends have a huge amount of work to do. Let's say you need to convert 1 million fibrinogen to fibrin. Is the best way to do it to actually sit down and crank it out? Or would it be more efficient to have each of you call 5 friends and invite those friends to come work, and ask those friends each to call 5 friends, and ask those friends to each call 5 friends? Well, obviously that would get the job done much faster, assuming you had those friends. And that's also what your body does. So actually it doesn't use these yellow guys to convert fibrinogen to fibrin. There's another player which does that, and it's an important one, so we'll give it a little drawing like that. And it is called thrombin. And thrombin, just like fibrinogen, is activated from an inactive form, which we call prothrombin. And the prothrombin has a little piece on the end that prevents it from working. So this is prothrombin. And that piece is removed when you want to get to work. So is prothrombin activated by the little yellow guys? Well, actually, he's not either, because the chain of amplification is much longer than that. To draw out the actual amplification cascade, you just need to see it and practice. But there is an easier way to draw it than it usually is drawn, and so we'll do that now. So let's say you were counting down from 12. Normally you would start 12, you'd go to 11, you'd go to 10, and then you'd go to 9. But let's say that you weren't very good at counting. You would start with 12, you'd go to 11, then you'd make a little mistake, you'd go to 9, then you'd realize you forgot 10, and so you'd go to 10. Now it's good that you remembered 10 because 10 is a big deal, and he's going to help bring us thrombin. Turns out that thrombin is also known as 2. And we know very well that thrombin helps give us fibrin, which is known as 1. And that's no surprise because fibrin's the most important guy, he's the ultimate goal, and thrombin is the guy that helps us get the ultimate goal, so he should be number 2. Now unfortunately it's not quite that easy. 10 likes 5 because they're both multiples of 5, so they work together. And 9 likes 8 because they're right next to each other, and so they work together. So this is the first part of our clotting cascade, and it turns out that we call this part here the intrinsic pathway. And we can talk about what that means later, but for now let's just give it its name. But what's perhaps more important to be clear about is that in this drawing, 12 is not actually becoming 11, and 11 is not actually becoming 9. What's happening is that 12, when it's activated, is a catalyst to convert 11 from its inactive form into its activated form, which we'll draw 11a. And then once 11 is activated, it serves as a catalyst to convert 9 from its inactivated form into its activated form. And so you see that these arrows are actually more about catalyzing. Now I said that this was an amplification sequence, and so I just wanted to share a little data to show that that's true. So it turns out that this guy, factor 1, or fibrin, in its inactivated form, which is fibrinogen, has about 3,000 micrograms per milliliter in blood, while this guy has about 100 micrograms per milliliter in blood. Meanwhile, 10 has about 10 micrograms per milliliter in blood, and factor 9 has about 5 micrograms per milliliter in blood. And so you can really see that as you go down this thing, you're increasing your amounts in your blood, which reflects the fact that you're also going to increase the number of active forms of these when you have a clot. But anyway, I said that this was the intrinsic pathway because there is another pathway which also leads to an activated 10, but in this other pathway what activates the 10 is an activated 7, which is activated by 3, also known as tissue factor. And I'll just write TF for tissue factor. And this pathway, which I'll circle here, and I apologize for the poor organization, this one is known as the extrinsic pathway. Extrinsic. So what's the difference between these two pathways? Well, it turns out that the extrinsic pathway is the spark. It's the one that gets activated by the original insult over here, whereas the intrinsic pathway is kind of like the workhorse that really gets most of the coagulation done. So how does that work? Well, you first get this tissue factor, which is actually one of these little yellow guys. And that tissue factor activates 7, which activates a little 10, so you get a shot, a spark that shoots down this way and activates a little bit of 10, and then 10 will activate a little bit of thrombin, and then thrombin will get the intrinsic workhorse going. And how will thrombin do that? Well, thrombin actually activates a whole bunch of these guys, and to remember the ones that it activates, you just need to take the 5 odd numbers starting at 5. So what is that? That's 5, 7, 9, 11, and 13. Actually, this is just almost right, but it actually turns out that it's not 9, it's 8. Because it couldn't be quite that easy. So those are the 5 that it activates. And so let's draw that in here in our drawing. So let's draw that in the form of blue arrows because thrombin is blue. We said it's going to activate 5. We said it's going to activate 7. We said it's going to activate not 9, but 8. So this will be an awkward arrow to draw. We said it's going to activate 11, and we said it's going to activate 13. Where's our 13? Well, we haven't actually drawn it in yet. So let's quickly chat about that. The end goal of this whole cascade is to get these fibrin molecules. And these fibrin molecules together will form some strands. But it actually turns out that there's one more step, which is to connect these strands together. And so we're going to want to connect these strands together with some crosslinks. These crosslinks will just hold them together so that they actually form a tight mesh. And it turns out that it's this step right here which is enabled by factor 13. And so let's draw the final thrombin activity, which is to activate 13. So you can see that once you activate a little thrombin, it's going to activate all the necessary things in this intrinsic pathway to get it going. And you might actually be wondering about 12 up there, because thrombin is not hitting him. And actually it turns out that if you remove a person's factor 12, they can still clot pretty well. And so it's clear that 12 is not a totally necessary part of this intrinsic pathway. And to be clear again with our use of arrows, this green arrow here is different from these white arrows in the sense that here we are saying that fibrin is going to become fibrin strands, which is going to become interlaced fibrin strands. So if this was all there was to the story, then every time you had a little bit of damage to your endothelium, you would cause the extrinsic pathway to fire, and so you would create a little activated 7, you would activate some 10, which would activate some 2, which is thrombin, which would start to create fibrin from fibrinogen, and moreover the thrombin would have this positive feedback which would cause more and more thrombin to be produced, which would cause more and more fibrin to be produced, and basically this system would just spiral out of control and you would become one large walking clot. So to keep that from happening, there are some negative feedback loops. And like much of the other steps in this picture, they're governed by thrombin. So one thing that happens is that thrombin helps create plasmin from plasminogen, much the way it helps create fibrin from fibrinogen. And this plasmin acts directly on these mesh networks of fibrin and breaks them apart. So that's one helpful factor, but that's not really an example of negative feedback because it won't prevent the continued production of all this. And so another example is that thrombin actually stimulates the production of antithrombin, which is kind of counterintuitive, but that's sort of classic negative feedback. And what antithrombin is going to do, as you could guess, is it's going to decrease the amount of thrombin that's being produced from prothrombin, and it's also going to impede the production of activated 10 from 10. So what if this whole system didn't work? I don't mean the negative feedback, but I mean the whole clotting system. Well, if it didn't work, then you wouldn't form a stable plug here, and you would get lots of blood pouring out of your damaged endothelium. And so what we call that is hemophilia. Hemo refers to blood, and philia means love. So people who have hemophilia love to bleed. And there are three different kinds of hemophilia. There is A, there's B, and there's C. And it's easy to remember the causes of these because A is associated with 8, B is associated with what comes after 8, 9, and C is associated with what comes after 9, not 10 actually, but 11. And so we can draw those into our clotting cascade over here to see that a factor 8 deficiency will give you hemophilia A, a factor 9 deficiency will give you hemophilia B, whereas a factor 11 deficiency will give you hemophilia C. And so we see that these guys target the intrinsic pathway.